Why is it doing that? I see. Ah, okay. Hi, everyone. Sound is okay? You can hear me properly? Okay. Oh, but it's totally blank. Okay, great. Okay, so after wrestling with Quercus for a while, we will not have a quiz today, but what I'll do instead is I'll send you the quiz that I intended to do in class, so you can do it at home and then submit it. Like I'll give you a day to do it, and you can submit it anytime in the next 24 hours. It shouldn't take you more than 10 minutes anyway.
And so will that be submitting to UConn, or will it be like a Quercus submission?
No, it'll be on Quercus. I just have to, yeah, I'll just get it to work properly. It just took a lot longer than I thought. Is that okay with everyone?
So there'll still be like the 10-minute time frame?
Yes,
Okay.
yes, that's right. Oh no, I'll give you more time.
Okay,
But
okay,
it shouldn't. But it's intended to be only 10 minutes.
Okay.
I'm not going to make it more difficult. That's what I was trying to say. Okay, so yeah, the purpose of it is just to check that you did the reading to some extent. Okay, wait, let me. All right, so so I wanted to give you the flavor of this topic of perturbation theory, and actually, it's kind of funny that, or kind of amazing that right now we're in the middle of a potential huge change in physics, right? And this change in physics has to do with the magnetic moment of the muon. So it's there's a discrepancy between the calculation of the muon magnetic moment and the electron and its actual measured value. Sorry. So it was a very famous agreement between calculation and experiment for the electron. In quantum electrodynamics, they were able to compute to a very high level of accuracy. I think that's 10 decimal places by now, the magnetic moment of the electron. But the muon apparently is not correct. The experiment is so precise now that they apparently believe that that there is no that it doesn't agree. It stops agreeing after 6 significant figures. And so that calculation that they're comparing everything to, that calculation is a perturbation theory calculation, which proceeds by a diagrammatic calculus, exactly like these calculations that we're about to do. And they just calculate a few terms, maybe around 6 or 7 terms at most. I don't really know the details. I doubt they have the capability of computing more than 7 terms, and then they use that to get their result, and they compare that with the experiment. Of course, the series is divergent, so you might wonder what in the world is what in the world are they doing? I mean, if they had the strength to calculate a few more terms, then it would really start to have disagreement with experiment. So I'm not sure what the meaning of that is, but anyway, I'm going to address that today. I'll explain kind of what's going on, or at least what they believe is going on. Okay, so we started with a series of very simple integrals. Integral of this is square root pi. We rescale a, change the measure, we get 2 pi over a square root. Then we add a source term, which when we complete the square gives us the same answer as before, multiplied by the dependence on j. Okay, and And the cool thing about this is that if I wanted to do this integral, but with a polynomial in front, then I could obtain it from this answer by taking derivatives with respect to j. Taking a derivative with respect to j brings the x in front. Taking it again brings another x in front, and so on. And so you can differentiate this answer to get other integrals. Okay, that's all I was saying. Remember that I explained. Yeah. So what we want to do is do this kind of integral, but with a cubic term there, or a quartic term, or some higher degree term than 2. And I explained the meaning of this. The meaning is all bound up with the choice of a contour. And here we have like 2 possible choices, or 3 possible choices, really, which are linearly dependent for the contour. Okay, so anyway, we have an integral. We want to approximate it in some way. So what we do is we take this badly behaved term, or the term we don't know how to integrate, and expand it out. And then we illegally integrate term by term. And so we have a sum of this to the k over k factorial integrated against the standard Gaussian. So we need to do a Gaussian integral weighted by a polynomial. That's what we need to do. And so that's what we want to figure out. Okay. Right. And that's what I was saying. So the first step is that we need to compute this. So each one of these terms is basically just x to the 3k times a bunch of factors, numbers. So if we can integrate x to the k e to the minus 1/2 ax squared, then we're in business. Okay, and then the idea was that I'm going to do it by differentiation. So if I take the derivative with respect to j, that's going to bring an x down. Let's see, what was I doing here? So this is the dependence on j. The derivative with respect to j is this, okay? And then on the right-hand side, I just actually compute the answer. I just take the derivative with respect to j of this. So if I take the derivative with respect to j, it's going to bring a j down in front, right here, j over a, okay? And if I evaluate this prematurely, if I evaluate this at j equals 0 right now, this is going to go to 0, and I'm going to get nothing, which is reasonable because this is an odd function and this is even. And so the integral should be 0. Okay, so then I move to the even case. Okay, and that requires taking 2k derivatives of f of j. Okay, and so what I tried to describe here was a kind of branching structure for the computation. That first we bring a j down, j over a. Okay, so every time this operator hits this factor, it brings down an a inverse j. Okay, now we apply the operator again, and it can operate on this as well as this, and so there's a sum of 2 terms. When it acts on this term, it kills the j that this operator brought down. So this operator and this operator, okay, they are pairing up to do a job. This one brings down the j, and this one kills the j. Take derivative with respect to j. And after they pair up, those two d by dj, they pair up, and they produce a constant in front, which when I let j equal 0, gives me an actual result. Here, instead of doing the job of kind of cleaning up the mess left by this guy, this one creates more of a mess by bringing the j here, and now we have j squared. And when we require j to be 0, this kills. Okay, so when we start applying this operator many times, the idea is that they have to pair up together. The only terms that will survive at the end, when I put j to be 0, are going to be those terms that arise when 2 of these differentiation operators pair up together. And when 2 of them pair up together, you will get a factor of a inverse. Okay, so when you see the x squared, that means that I need to take d by dj squared of the operator with j. That's going to be two operators, and there's only one way for them to pair up. You bring down the j, and I'll kill the j. And then we got a to the minus 1. Okay, so a good way of organizing this, and this is the way that it's organized in statistical mechanics and in quantum field theory, is that these calculations you always compare with the bare result, the so-called partition function. You just divide the integral of the operator that you're interested in, x squared, and then you divide by the integral without anything in front. And this gives you a kind of interesting way of computing the inverse of the number which occurs in the exponent. Okay, so this is our simplest. This is our simplest calculation. And I'm going to denote it by a diagram in the following way. I'm going to say that I'm applying, this is the first factor of x, and this is the second factor of x, okay, in the x squared. And or you could think of it as d by dj, and this you could think of it as d by dj. Okay, and there's two operators acting, and they've got to be paired up. So when you pair them up, you draw a line joining them, and you draw a inverse joining the two lines. So because we have x squared, I draw two dots. And because there's only one way to pair them, I say that the answer is A inverse. So you see, I'm converting it into a stupid diagram, which kind of encapsulates the calculation that I just did. Okay. So, okay, so now let's continue with this. Let's say that I want to, so part 2, okay, let's compute x to the 2k, which is the integral x2k e to the minus 1/2 ax squared over e to the minus 1/2 ax squared. And okay, and so this is, I'm going to have here a whole bunch of, I'm going to have 2k. So this will be, if I write this out, this will be dj to the 2k applied to f of j with j set to be 0. And so what we need is all of the contributions that come from pairs of these operators operating together. So, for example, if I write it like dj, let's just do another example just to emphasize this. So I'm going to get 1 over f0 times del j applied to fj at j equals 0. So so this is, again, remember, this is e to the j squared over 2a. And when I take, so the question is, what is going to happen? So once I apply this operator, I'm bringing down a j. Then this one, okay, will produce, so this will, the first step, let me just draw them like this, it's going to bring down a j. The next step is going to over a. And then I'm going to get a inverse fj. Let me just simplify the notation here. Okay, but there's also another term in the sum, which is a inverse j squared fj. Okay, and then this one will continue. if the J acts on, if the J acts here on the first, on the thing in front, sorry, I'm just missing a factor. Yeah, so I'm going to get an A inverse. Okay, yeah. So here I want to make a small kind of pedantic point. Okay, it's just going to be helpful. So the question is, when I apply this J to this, there's a possibility, it can't do anything to the A inverse. However, it can bring down another J. Okay, and this one can, of course, also bring down another J. Okay, but the one I want to comment on is this one. When I apply d by dj to this expression, which of the two factors in front is it going to act on? Well, instead of writing 2 times this, right? What I'm going to do is just write a sum. There's actually 2 possibilities. It could act on the first, and I'll get A inverse times A inverse J, Fj, or it could act on the second. Okay. The reason that I want to separate these 2 possibilities out for the derivative of this term is because in this case, you see that this operator paired with this operator, the one that brought down the first A inverse J. Whereas in this term, this operator paired with this one, right? So there are 2 different pairings corresponding to the 2 different positions of the A inverse. Now, of course, these are the same term, so they add up to just 2 times the same term, but they are different pairings. Okay, so these are different pairings. Okay, and then what? Well, okay, so there's going to be, I could bring down another J, but that's going to be useless because I need to set J as equal to 0 at this point. So I just want the terms that are going to get rid of J. So this is going to be A to the minus 2 F of J, or F of 0. So this will be a term. And each one of these, I can bring down another J, but those will be going to 0. This will be A to the minus 2. This will be A to the minus 2. Those are 2 more terms. And this one is kind of hopeless. There's nothing that we could do. We only have 1 more J, and there's too many J's left over, and it's going to die. So it looks like what I'm getting is 3 times A inverse. A kind of an interesting result, that the expectation value, this integral with x to the 4, gives me 3A inverse. Okay, so this disaster of a calculation is encapsulated by the following diagram. We have 4 copies of x. And the question is, how many different ways can we pair them with each other? Okay, so the one possibility is to pair them like this. Oh, I'm sorry, I wrote the wrong thing here. It should be A to the minus 2. Oops. Okay, so this is one possible way of doing it. From here to here and here to here. Or it could be from here to here, and therefore from here to here. Or it could be from here to here and here to here. And each one of these contributes A inverse. So this diagram evaluates to A inverse multiplied by A inverse, which is A to the minus 2. And this one contributes A to the minus 2. And this one also contributes A to the minus 2. So we have a sum of a finite number of diagrams, each contributing A to the minus 2. And so we get 3A to the minus 2. Okay? This is the heart of the diagrammatic method. Okay? That's one way of seeing it. I mean, there's many different ways of deriving it. But anyway, this is okay. So let's do the general case. Oh, do I want to make? No, that's fine. Yeah, that's good. So the general case is x to the 2k. This will be so how many? So there are 2k dots, and I'm going to have to pair them. And so that means that really there's k pairs. And each of the k pairs contributes an A inverse. And so that's going to be A to the minus k multiplied by the number of pairings. Okay, so how do you count the number of pairings? Well, okay, you have to start with 1 so that you count it as the first one. So I have 2k dots, and let's say my first pairing is going to be this one. The pairing where we just pair 1 and 2, 2, 3 and 4, 5 and 6, and so on. So this is one pairing. This counts as one pairing. And now the question is, what group is acting on this pairing, on the space of pairings? So this is a pairing in the set of all pairings. Okay. You understand what I mean by a pairing, right? We have basically like an ordered set, and we want to put them into pairs. We want to partition it into subsets of size 2. And the question is, how many such partitions are there? So this is one of them. And what group acts on these things? Well, you could apply the permutation group on 2k objects, and you could, apply a permutation, right, to these dots, and then you'll get another pairing. So any other pairing may be the set P of pairings. Any other pairing may be obtained by acting by S2k, the 2k symmetric group, and the stabilizer of this P0 is what? It's in order to stabilize this pairing, I would need to preserve the fact that these are pairs. So that means that if I take this pair and switch them, right, then it's the same pairing. Or if I take this pair and switch them, right? So this means that there is an SK where we permute the K pairs, okay? And there's also a Z2, which is that I could permute the individual elements in a pair. And so this will be S2 to the K. This is the stabilizer subgroup. And okay, and so this means that P is isomorphic to S2K mod SK cross S2 to the K. And the size of P is just the quotient of the sizes of these two groups, which is 2k factorial over k factorial multiplied by 2 to the k. Okay. So we get the answer is x to the 2k is equal to a to the minus k multiplied by 2k, k, 2 to the k. Okay, and this is very typical for Feynman diagram calculations. You often get these factorials and powers and quotients of factorials and so on. Okay, so this is...
Sorry, just a question.
Yeah.
What do you mean by isomorphic here? Like what structure
What do you think
is on...
I mean? What do you think I mean?
I don't understand what structure is on the set of all pairs.
What do you think the structure is?
A set?
Okay, then that's good.
Okay, so
You have
just...
more structure, but it doesn't matter what...
Okay, because the thing on the right looked like a group, so I was just thinking, okay.
Well, it's a quotient of a group by a subgroup, so it may not be a group.
Okay, got it.
The set. It also might be a homogeneous space, but it's irrelevant. The point is we just need a number. We just need to count it.
Yeah.
So the set structure is all that's important. Okay. So this gives us enough information. This allows, well, okay, so first of all, this tells you how to do these integrals. This is just like integrals that you maybe didn't learn when you were learning integrals. But this allows us to compute this function that we wanted to compute. Right. We wanted to compute this. Okay. So let's see how we arrange our calculation to get this result. Okay. Right. Okay. So let's just do this by expansion. So we're going to have this 1 plus b x cubed okay, and right. Okay, and we already saw that the odd powers do not contribute. So the odd powers do not contribute, but the even powers do. And if we write this out, we're going to get the integral for b equals 0 is going to be multiplying, whenever we computed this this integral here, this thing always appeared in front. And so for the expectation value, we divided by it. So here, the same thing is going to happen. This factor is going to appear in front of each result. So the first term is going to be the integral of 1, which is just z0. And so I just put a 1 here. And then this one is going to be 1 over 2 factorial b over 3 factorial squared. And then I have x to the 6 expectation value. And then the next term will be 1 over 4 factorial b over 3 factorial fourth times x to the 8, and so on. Okay, so that gives us the answer we want. And so we can just complete the calculation. We get z0 times the sum k greater than or equal to 0, b to the 2k factorial, 3 factorial to the 2k, a inverse to the 3k times 6k factorial over 3k. Here's our results from before. 3k factorial times 2 to the 3k. Sorry. And this is a power series in B. Okay, so by doing this illegal operation of one way that you can see that this is illegal, okay, like obviously illegal, is that none of this depended on the choice of contour. We just used the usual Gaussian contour along the real line in order to evaluate all of these. Okay, so we're not even picking a reasonable contour, and yet we got an answer. And it turns out that this answer is definitely not convergent, because if you look at the behavior with respect to B, when the power of B grows, what we have is a 6k factorial over a 2k factorial and 3k factorial. So you can use, if you want, you can use Stirling formula to approximate this for large K. The point is that it grows like K factorial, because this is 6 and this is basically 5. So this thing grows as the coefficients grow as K factorial. So this does not converge. Okay. And this is, okay, so what is the situation? So what I'm about to say, what I'm about to explain, is that this is what's called an asymptotic series. It's an asymptotic approximation to the function. And the point is that we have a perfectly well-defined function. This integral is very well-defined. It's a function of B, and it's analytic away from B equals 0 and away from certain loci in the B plane. Okay, but generically, it's an analytic function, perfectly well defined. Okay, but we are expanding it about a bad point, and that's resulting in a divergent series. And yeah, and so the difference between this and what's happening in physics, in real world physics, is that in real world physics, they do not have the function that is well defined. All that they have is this thing. And for the same reason that this thing grows too quickly to converge, similarly do the ones in physics grow too quickly to converge. It's very easy to show. It's not a very deep result, okay? And so the assumption is that the things that they are calculating are an asymptotic expansion of something that is well defined, but that thing which is well defined is not known. Not defined, it's not known, okay? That is the difference between, so what we've seen here is non-perturbative is the integral along C of, it's f of B, like along C e to the minus 1/2 ax squared plus b x cubed dx. So this is a well-defined. And then perturbative is this f hat b. I'll call it f. Sorry, I called this f last time. So this is f hat b, fb. And so this thing is, we should call this f hat b. And this will be f of 0 and f of 0. Okay, any questions about this result?
So yeah, I have a question.
Yeah.
These f of b's, like you're saying, in physics generally, you don't have them, but you assume that this is like the asymptotic expansion of something that might be well defined.
Yes.
So when we did like the hydrogen atom, I think you mentioned at the beginning, like that's like one of the nice examples of a solvable system in quantum mechanics.
Yes.
So for that, we would have this function f of b, or do we still have to calculate things perturbatively like this?
In the case of quantum mechanics, yes, you have the function. Yeah, that's right. In the case of quantum mechanics, we know, yeah, quantum mechanics is perfectly well defined. I mean, there's no mathematical problems with it. It's basically like saying if we change the potential function in the hydrogen atom and you find the new energy levels, that's whether it's solvable or not is not important. It's a Schrodinger equation, and the Schrodinger equation has solutions, and we know what it means. We know existence criteria for solutions of these PDEs. In quantum field theory, it's not about that. In quantum field theory, it's not that you're trying to solve a PDE that is difficult. No, it's that you don't even know how to define the quantity in the first place. So it's quantum mechanics is a special case where everything does actually make sense. But at the end of today's class, I'll show you a famous paper where in quantum mechanics they actually compared the true result with the asymptotic series, and they showed that it is an asymptotic series. And anyway, I'll get to that in a second. So, okay, so there's something about this calculation that I want to say. Important thing about the calculation. So if we look at this calculation, you see that I was careful to keep the interaction term always visible, and I didn't expand it out and have just factors of x, right? So in other words, this interaction term, when you expand this out in the exponential, it occurs here always as a single unit, maybe raised to a certain power, or something is done to it, but it's never decomposed. It's always present as a single blob. Okay, the interaction term. And we know that because there's an x cubed, we're supposed to draw 3 dots as part of our calculation, or in this case, we draw 6 dots, right, in order to do the matching. So because these 3 dots that come from this term, because they always occur as a blob, right, what we do is we take the 3 dots and we make a new type of dot, okay, which is called an interaction vertex. Okay, so now instead of drawing, so now the idea is that, for example, if we go back to our calculation of x cubed squared, right? This is x to the 6th. Normally what I would do is I would just draw 6 dots and I would start, pairing them in all possible ways. Okay, but instead of doing that, what I'll do is I'll take 3 dots and join them together in one big dot, and I'll put 2 of them. It's the same exact thing, but I'm just keeping them separate and joining them together because they occur as one unit, which is the interaction term. Okay, so what's going on is that instead the picture could be like this, that you have 2 interaction vertices. There's 2 interaction vertices. Because of this 2. Okay, and each of them has 3 spokes on them, or in other words, each of them counts as 3 dots. Okay, and then what I'll do is I'll join them so that each of the 3 is used up. So this would be a matching. Okay, if I zoom in to this, what you see is really that there's 3 dots. Coming into my interaction vertex. Is that clear? And here we have another one. Okay, so let's see what happens. So so if I organize myself like this, let's say, then okay, hopefully that's enough. Okay, so it looks like birds have been walking around. Okay, so for example, this would be the first standard pairing. Okay, another one would be this one. Another one would be this one. Okay, and all of these they were chosen so that the spoke, the red line that goes to the other side, it goes to the first leaf, but it could also go to the second leaf. You see how it all works. I just want to see if I wrote down. So all of these graphs are going to be present, okay, and they must be counted, and of course each of them is coming with a to the -3. Now, let's see. Did I miss? So all of these graphs have something in common, which is that they all look like this. This is a dumbbell graph. Did I get all of the dumbbell graphs? I don't think so. which is the, basically I just need to pick one of these three leaves and one of these three leaves and join them. So there's 3 choices times 3 choices. So there should be 9. So this was 1 going to the first, going to the second, and, oh, well, that's the one I missed, is the one that goes to the third, this one. So all of these are all going to add up together to 9a to the minus 3. But there are other graphs, because I could also do this. I could also pair them like this. Right? And then I could permute these. Right? And so on. And these will have a different topology. The graphs will look different. This is called the theta graph. These are the two, well, some of the most famous Feynman diagrams. Okay. So the idea of Feynman, so Feynman's idea, which is now quoted as a theorem, okay, Feynman's idea is that instead of laying out your interaction vertices and then counting all possible matchings, what you should do is reorder the sum so that you sum only over the different topological types of graphs, right? So in other words, we're going to notice that, you know, when you have 2 interaction vertices that are trivalent, and this is because the interaction is bx to the cubed, right? Then there's only 2 types of graphs you could possibly create with this type and this type. Okay, and you just need to know the proportion of, you know, how many times does this one occur versus how many times does this one occur. So he's counting it in a different way, right? He's counting it based on the graph type. So the idea is count the matchings by first, by A, determining what kinds of graphs may occur, and B, determining the proportion, you know, the frequency or multiplicity of each graph. Okay, and then we will get a sum that way. So the yeah. Okay, yeah, that's fine. I can do this. There's plenty of time to do everything I wanted. Okay, great. So right, okay. So let me state the theorem carefully. Okay, so the theorem is that ZB over Z0 is equal to a sum over graphs. We're going to have a bunch of edges in this graph. And every time we have an edge, we're supposed to put an A inverse. So that means that the power of A inverse will be the number of edges in the graph. This means edges. Okay, and then every time there's notice that every time there's a vertex, we have to put a B, because that's the interaction vertex. I mean, it's B over 3 factorial. And the reason that that 3 factorial was put in there was because here what's going to happen is that B will occur without any factor in front. And it will be B to the power of the vertices of gamma. This is the number of vertices. This is the number of edges. Okay, so far that is pretty simple. I could have told you that much easily, right? Because we know that when we build it, there's going to be each edge is a matching, and that matching costs a to the minus 1, and every time there's a vertex, there's a B. The interesting thing is that what happens right in front is that you get 1 over the size of the automorphism group of the graph. And that is the result. So this is just coming from a simple recounting. Anyone in this class could prove this result. You just need to reorder your counting. But I need to explain, in order for you to prove it, I need to explain what the graphs really are and what it means that it has an automorphism group and how to compute the automorphism group. Okay, so in order to understand this, I need to define what a Feynman graph is. So a Feynman graph is a triple H, PE, and PV, where H is a set of half edges, so-called half edges, and half edges are exactly what they sound like these things here. These are half edges because they are going to be joined together by an edge. So you could just imagine cutting each edge into 2 halves. Okay, and so we have a set. In this case, there's going to be 6 elements of the set H. And this set has 2 partitions, PE and PV. This is a partition of H into 2 element subsets. And these are called edges. Okay, so for example, one way that I could partition them into 2 element subsets could be like this. This is one partition, PE, the edge partition. Okay, and then this PV is the partition of H into 3 element subsets. Actually, in general, it would be greater than or equal to 3 if there were interaction terms of higher valency, but in our case, it will be just 3. And these are called vertices. Okay, and an automorphism of gamma is a map from gamma from H to H, which preserves the partitions. Remember that a partition is a decomposition of a set into a union of disjoint subsets. So an example would be, this could be a vertex and this could be a vertex. So this would be PV. And the corresponding graph to this one would be the theta graph. Whereas the dumbbell graph is a non-isomorphic graph where we have the vertices, could think of them like this maybe, and the edges, you could think of them like this. So this corresponds to this. Okay. So it may seem pedantic to describe a graph this way, but it's very important because we need to know exactly what the structure is for this combinatorial object, because we need to compute its automorphism group. And so, yeah. So, okay, so what is the automorphism group? Oops. So let's compute automorphism group. Oh, I didn't give this as an exercise in the assignment, did I? Computing the automorphism group of the dumbbell and the, okay. So, so the automorphism group of the dumbbell. Okay, how do you figure this out? Well, you should look at this thing as having, 1, 2, 3, 4, 5, 6 half edges, and the partitions are visible, right? So, for example, I cannot take these 3 elements and separate them. They need to stay together. So these 3 elements could be sent here, or they could be sent to themselves, but you can't split them up. Okay, so basically we can see some parts of the automorphism group. So we can flip these 2 half edges without changing the graph, and we can flip these 2 half edges without changing the graph. And then the last thing we can do is switch these 3 with these 3. And that's basically all that we have. So this is going to be a Z2 cross Z2 cross Z2. Actually, I think there's a semi-direct product in here somewhere, but it doesn't matter because all I need is the size. And the size is 2 to the 3, which is 8. So this factor will be 1 over 8 times a to the minus 3 b to the 2. That's the term, that's the evaluation of the Feynman diagram. Each diagram corresponds to a numerical result, which is made up of the given data, like A, B, and some numerical factors which depend on the graph. Okay, automorphism group of the theta graph. What is it? Well, we have, yeah. So again, well, it's clear that these edges, I can permute them. So there's an S3 for permuting these edges, and then there's an overall Z2 which switches this partition. So there's an S3 cross Z2. And the size of this is exactly 12. So the evaluation of this will be 1/12 with the same thing, a to the minus 3b squared. It's the same number of edges and the same number of vertices. So in the end, z of b will be over z of 0 will be 1 plus, and then the first term will be with 2 interactions. You cannot have a single interaction vertex, right? If you had a single interaction vertex, there would be a leg that is sticking out and that is not being contracted with anything. So there is no contribution from the single interaction. So this is going to be plus 1/8 plus 1/12 which is 5 over 24 times a to the minus 3 b squared plus something of order b fourth. Okay. So you do all of this combinatorial work in order to figure out your coefficients, and you get this infinite series, and that's how it works. So that's a crash course in Feynman diagrams. Any questions about this?
What is this actually computing? Is this the interaction of two electrons or electron with itself, or what would be the physical significance of this calculation?
Well, yeah. So this is it's a toy model from the very beginning, right? So if you want, you could think that this x squared is the dynamical object. Like it's the it's difficult to answer your question because this is actually a zero-dimensional quantum field theory. So space-time in this case is a point, and x is a field that has a value at that point. So it's a point in the real line. X, it takes values in the real line. So you could think of it as a point moving along a line and interacting with itself. Okay, and you could think that it's like you're computing the expectation value of scattering amplitudes of the particle acting on itself somehow. But yeah, it's difficult to say that there's a physical meaning to this because it would mean that space-time has dimension 0. So it's not even clear. Yeah. But anyway, the mathematical structure is what I'm saying is that it's the same. That in quantum field theory or even in quantum mechanics, when you write it in the path integral formulation, you are computing these integrals. Anyway, so for now, don't worry too much about what the physical meaning of it is. You will eventually learn that. So in the assignment, I asked you to figure out the next order in perturbation theory. So that means that there's going to be a whole bunch of graphs that are going to contribute, and each of them is going to have a symmetry factor. That's what this automorphism group is called. And then you'll be able to find out the next term. Okay, so what I want to explain now is what is the usefulness of such divergent series? Why are they helpful at all for anything? Okay. So what is the meaning of this divergent series? The answer is that it is an asymptotic expansion of f of b as b approaches to 0 from the positive real axis side. There's a sector actually where it can, I don't remember what the sector is. It's probably, yeah, I don't remember. But anyway, this is what this thing is. It's an asymptotic expansion. So I just want to kind of expose you to what asymptotic expansions are in maybe the most important example of asymptotic expansion. So let's speak about one example, an important example, which is called the Stieltjes integral. Okay, so this integral looks like this. It's a function of x, which is defined as a line integral of an expression like this, dt. Okay, and let's draw a picture of the t-plane where this integral is happening. So it's happening along a contour which is starting at 0 and going off to infinity. Okay, and and the integral, this integral has a parameter in it, which is x, and the result of the integral is a function of x. And so we would be interested in knowing how this function varies with x. Now, depending on the value of x, so let me draw the x-plane. And let's say that x was equal to 1. So if x is equal to 1, then this is 1 plus t. And 1 plus t has a pole at t is equal to -1. So the pole here is t equals -1 over x. So if x is equal to 1, this pole will occur here. And therefore, that's okay. I don't care if there's a pole there because my integral does not touch it. Okay. And then if I let x go somewhere else, so see, let's say x equals I, then -1 minus 1 over I is going to be minus I guess. -1 over I. Yeah, it's I. So therefore my pole will be here. Okay. And then if I start moving this, there's going to be a problem because as I get closer to the negative real axis, this pole is starting to interfere with my contour of integration. And when I get to that negative real axis, there is a major problem in the definition of the function. So this is a cut. F of x is not defined here. But it is perfectly analytic and well defined elsewhere in the complex plane, which for me is always yellow. I don't know why that is. It's probably because I learned complex analysis from a graduate text in math. Okay, so this function is an analytic function on the complex plane with a branch cut singularity at the negative real axis. And I just explained to you why that is. Okay, and so we want to find a nice approximation to this function, and it's so typical of people that in order to do that, what we're going to do is expand it about the best possible point you could choose, namely the singular point at 0. So we're going to ignore your better judgment, and instead of expanding it about these nice analytic points, which have beautiful convergent power series, we're going to expand it about this point. So let's expand about x equals 0. So what does this mean? Well, what it means is the following. So we can do this. So let's rewrite f of x. So f of x is integral 1 plus xt inverse f of, e to the minus t. Oh, I should have said that there's no question at all that this is a well-defined, absolutely convergent integral, because look at the numerator. It's dying extremely fast out at infinity. So this thing, it could do whatever it wants. It's not going to win when it comes to the exponential dampening out at infinity. So this is absolutely convergent. There's no issue. The problem is just that the domain of, the contour will be broken by the pole, and so it won't be defined. Okay, so then what we could do is we could expand this out. Okay, and so I could write it like this. So you could write it as 1. So if I expand this out, the first term is going to be like 1 times e to the minus t. And if you integrate e to the minus t from 0 to infinity, you're going to get like minus e to the minus t evaluated at the endpoints, which is basically going to give you 0 minus 1. So it'll give you 1. So the first term is just 1 by integrating the exponential. And the next term is going to be, you're going to have like this expansion is going to be 1 minus xt plus xt squared. Okay. And so then you're going to be integrating e to the minus t times this, right? And so the next term is going to be an integral of xt e to the minus t, and the x just comes out. So I'm going to get minus x times the integral from 0 to infinity of t e to the minus t. Well, plus the rest, plus so to simplify things, let me just simplify it this way. I'll say that it's 1 plus xt to the minus 2 e to the minus t dt. And let me just write the next step in the integration by parts that gives a kind of clever way of rewriting this. 1 minus x plus 2x squared to the minus 3 e to the minus t. Right? Because if you think about integrating this by parts, you're going to get minus 2, the derivative of this term is going to give you this, and the derivative of this term just gives you itself, but with a sign. So by integration by parts, we can increase the power here. We can continue to increase the power. 1 minus x plus 2x squared minus 3 factorial x cubed minus 4 factorial x fourth. Okay, plus an error. And the error, let me just write the error, is minus 1 to the n factorial x to the n integral of 1 plus xt to the minus n plus 1 power e to the minus t dt. And this should be plus n factorial x to the n. Oh, sorry, n minus 1. Okay, so this does not seem to be a particularly useful way of going about this calculation, because we're getting what could not be a more obvious divergent series. So we're getting a formal series, which is the sum of minus 1 to the n factorial x to the n. So I don't know about you, but that does not look like a convergent series to me. Okay, now so let me explain now what's so this is always a bit difficult to explain, but so this is a true fact, right? If I terminate at a finite n, then f of x is this polynomial in x plus this crazy function, which is basically just f of x minus this polynomial. I'm not saying anything, right? I'm just saying that there seems to be this polynomial, and then we have this error term, which has this particular expression. Now, if I if I have a very small value of x, so suppose x is like 0.001. Okay, and then I just evaluate the terms of the sum, which is n factorial x to the n. So this is n factorial x to the n, and this is no, sorry, this is n, and this is n factorial x to the n with x equals to 0.001. Okay, so I should probably just bring it up on Sage or something and calculate it in front of you, but instead I'll just show you what it looks like. So at first, well, the first term is just 1. Say 1. And then the next term is x, so it's going to be, and then the next term is going to be even smaller than that, smaller than that, smaller than that. Okay, but then there's going to be the n factorial will win out. Okay. And this region here is what the physicists are aiming for. Okay, so the idea is that there's an intermediate range where you can say something about how this polynomial is approximating the function. Now, the problem is that if you take more terms, you're not going to improve your estimate. Okay, there's a certain number of terms that gets you closest to the answer. But that implies that there's a lower bound on how much precision you could possibly have. Okay, so why does this occur? Why does this region occur at all? And why is it any good? I mean, who cares if the terms are getting small? Why should that matter? Why should it mean that the polynomial is getting closer to the true answer, right? So the reason is by an error estimate. So if we look at this error, let me just grab the error. Oops. So if I look at the error, then I can see that this term here is for x greater than 0. This is like 1 over, let's see. And because I'm integrating along the positive real axis, this quantity in here is greater than 1 for x greater than 0. And then I'm taking 1 over that quantity. And so that means that this integral is going to be smaller than the one where I replace this by just 1. And then if I replace this by just 1, then I have this integral here, which is just 1. So this integral here, for x positive, it's bounded above by just 1. And so I can conclude that as x, let's see. Let's see how I want to say this. So as long as x is positive, the error, I can bound it by n factorial x to the n. Okay, so this is just a simple estimate from this, and notice what this is. This is the next term. The next term in the series. So this error is actually less than the error between this polynomial and the actual function, okay, is measured by the size of the next term in the sequence. It's a funny thing, but this is how asymptotic series behave. So the error at the nth partial sum is bounded by the size of the next term. So if you look at the size of the terms, look, the size of the terms is going down, down, down at first. And then the terms get big, which means the error gets big. But this here would be the best place to stop. Just stop doing your sum, do the first term, the second, the third, fourth, fifth, and then stop. Okay, at that point, the error will be bound. Well, okay, maybe you should stop at the fourth. Then the error at the fourth term will be bounded by this point, which is the smallest one. Okay, and that's the best that you could do. So for a fixed evaluation at x, okay, so if x is chosen, there is an optimal place to truncate the series and an estimate plus an estimate of how big the error is. So so this is what asymptotic series are. Okay, and look the other thing that you should see is that this thing depends on x, right? So if you want to get the error smaller and smaller, all you need to do is let x get smaller and smaller. And you can get arbitrary precision in a sense, but you have to evaluate somewhere else. Okay, so I mean, but the problem is that this this x for us is b, and b is the interaction strength. And in physics, unfortunately, you cannot choose this interaction strength. It's just given to you by nature. So, this thing is a power series in B, and we're, B for quantum electrodynamics, B is what is called I forget now, E squared, and this is 1/137. It's a number. And it's lucky that this thing is small, okay? And so that means that we're going to be looking, so the idea is that QED should be very accurate, perturbative, QED should be very accurate as long as the terms n factorial 1/137 to the n are small. But if you sum more and more Feynman diagrams, eventually the n factorial will win, and you will be at the maximum precision of physics in the perturbative sense. So this means that there is an a priori lower limit. There's an a priori precision. There's an a priori limitation on the there's an a priori limitation on the accuracy of perturbation theory. And I just wanted to kind of demonstrate this in this example. So this will be very accurate, a very accurate description of that complicated transcendental function, this f of x. Usually when you use Mathematica or better Sage to compute these special functions and compute their values, almost in all cases, it is done by such a perturbative series. It's way more accurate. It has way faster convergence in a limited sense than Taylor series. Taylor series are extremely slow and should never be used. With this type of thing, you get very quick answers. They have a lower limit on their accuracy, but anyway, usually that's way beyond what you're needing. Okay, so is this clear now? What I mean? So this is part of a subject which is called asymptotic series. And this is a very well-developed subject. You begin by learning about Poincaré asymptotics. And then you go on to learn these things which are called Gevrey asymptotics. And it's related to this subject, which I find very interesting, which is called resummation, which is an attempt to sum the divergent series. There's a small community in physics that believes that it might be possible to use mathematical techniques to resum this divergent series and obtain the analytic function. I've done some work on those in the past few years. But anyway, that's the status. So I just want to show you any questions about what I presented. I just need to bring up a paper so you can ask me any questions. I want to show you two amazing papers. It's supposed to be somewhere which, I'm looking where I put it, but I'm not finding it. Let me just go get it. If someone can find it, I'm looking for a paper which is called The Difficulties in Quantum Electrodynamics. And it's by Paul Dirac. And it's like disappeared from my computer all of a sudden. And I think it's in 1940, 40 something. The Difficulties in Quantum Electrodynamics. Yeah, it's frustrating if I can't find it in time. No one had any luck yet?
I had a look on Google, but it doesn't seem to show up immediately.
Yeah, I looked on Inspire in the physics archive. It is listed, but they don't have any links to any publications. It's just there, sitting there. It's basically an orphan. Let me just check
What
one.
journal is it in?
London Physical
Yeah,
Society, I think.
I'm looking at.
Maybe this can be part of the assignment.
It's not development in quantum electrodynamics.
It's a 4-page paper.
Okay, yeah, no, this is like 2 pages.
Okay, instead, it's unfortunate. I can tell you what I remember from the paper, though. So, and let me share the other paper. Okay, so in Dirac, basically, he was the one who understood the processes, the calculations that Feynman, Schwinger, and Tomonaga were doing in order to get these very accurate descriptions of the magnetic moment of the electron and other related calculations. And so he developed this perturbation theory, and he spent 4 years trying to prove that the series converges. So he said that he worked harder on this problem than any other problem in his life. And at the end of this 4-year period, he realized that it was completely obvious that the thing could not possibly converge, and that in most physical theories, it can't converge. And he had a very nice, he had even a physical proof of the, of the fact that, I found it. Just saying what I just said reminded me what directory it was in. Okay. This is an amazing paper. So this is a paper from 1951. An argument is presented which leads tentatively to the conclusion that all the power series expansions currently in use in quantum electrodynamics are divergent after the renormalization of mass and charge. The divergent in no way restricts the accuracy of practical calculations that can be made with the theory, but raises important questions of principle concerning the nature of the physical concepts upon which the theory is built. Okay, this is a problem that was identified by Dyson. That's the reason why I kept saying that it was Dirac. It wasn't Dirac, it was Dyson, of course. I was thinking Dyson and searching for Dirac. Such an idiot. So this is what was developed by Dyson. Dirac was too old at that time. Dirac is the previous generation. So Dyson is the one who figured out perturbation theory, and he also tried for 4 years to prove that it converges. And he failed, and this is the paper that proves, it's a 2-page paper, I'm sorry. I remembered 4 pages because there's 4 columns, 4 sections. So, right. So he gives an argument, which I'm not going to repeat, but it ends with nevertheless, because of the quantum mechanical tunnel effect, there will always be a finite probability that in any finite time interval, the system will find itself in a pathological state. Every physical state is unstable against the spontaneous creation of large numbers of particles. A system once in a pathological state will not remain steady. There will be a rapid creation of more and more particles, an explosive disintegration of the vacuum by spontaneous polarization. In these circumstances, it is impossible that the integration of the equations of motion of the theory over any finite or infinite time interval, starting from a given state of the fictitious world, should lead to well-defined analytic functions. Therefore, f of minus e squared cannot be analytic, and the series cannot be convergent. So he's basically saying that if the series were convergent, there would be a region of convergence. This region of convergence would mean that the theories for negative coupling constant would be well defined, but they aren't, because the universe would explode if with the negative coupling constant, and the calculations shouldn't converge. So it's a very difficult argument. Let's put it that way. But the result is valid. So the thing that I want to point you to is the conclusion that he reaches. And this conclusion is really amazing that he wrote this in print, because this conclusion describes the state of physics to this day. he says, if the conclusion of the foregoing argument is accepted, then there are two alternative possibilities for the future development of quantum electrodynamics. Alternative A and alternative B. Alternative A, there may be discovered a new method of carrying through the renormalization program, not making use of power series expansions. In this case, every physical quantity will be well-defined and calculable, and the series will be an asymptotic expansion for it in the limit of small e. Since Fe squared is not analytic at e equals 0, the asymptotic expansion will not be sufficient to determine the function uniquely. The additional information necessary to determine Fe squared will be obtained from the existing formalism, using no new physical hypotheses, but only some improved mathematical methods. Okay, that is what physicists have been trying to do since that time. It's called finding a non-perturbative description of the theory. A non-perturbative description of the theory. And one of the holy grails of string theory is supposed to be that it is supposed to be some kind of avatar of some theory that is non-perturbative. And the reason that I say that is because there's several results of string theory that are non-perturbative in their nature. They give relationships and facts about quantum field theory which are not coming from perturbation theory. And that's why string theory is the major source that we have of non-perturbative information. It doesn't mean that it's a theory, but it just means that we are getting some kind of non-perturbative information from string theory. Okay, alternative B. All the information that can in principle be obtained from the formalism of quantum electrodynamics is contained in these coefficients, which you get from Feynman diagram expansions. By the way, each diagram, okay, when we wrote down our diagram, it was very simple to determine the coefficient in front of the b to the 2k, 3k term. In the case of quantum electrodynamics, it's the evaluation of the Feynman diagram itself, which becomes a little bit more complicated because you need to do an integral over a finite dimensional space, which is not compact. And that's what he's referring to as renormalization, is that it's a little bit more difficult to define how to obtain that coefficient. But that's not a big deal. It's not as big a deal as the fact that the whole series diverges. He's talking about, when he refers to this renormalization, it's all about finding the actual coefficient, which for us was very easy. So, okay, fine. So he's saying alternative B is that that's all there is, folks. In this case, the quantity Fe squared is neither physically well-defined nor mathematically calculable, except insofar as the asymptotic expansion gives some workable approximation to it. In order to define Fe squared precisely, not merely new mathematical methods, but a new physical theory is needed. And then he says, this is hilarious, the last paragraph of Dyson, I think he recently died. I think it was last year or something like that. Anyway, it's an amazing paragraph. He says, I wish to call attention to the attractive features of alternative B in the present state of physics. If B were true, it would imply that quantum electrodynamics is in its mathematical nature not a closed theory, but only a half theory, giving insufficient information for the exact prediction of events. Experimentally, we know that the world contains one group of phenomena which is accurately in agreement with the results of quantum electrodynamics, and another group of phenomena which is not understood at all. We need to develop new physical ideas to understand the second group, and still we cannot abandon the theory which successfully accounts for the first. If quantum electrodynamics were a closed theory, this would be a difficult dilemma. But if the theory itself leaves room for new ideas, no such dilemma arises. So yeah, he's somehow saying that that it might be a good thing that it's not completely closed, because in a way, if it were completely closed and it doesn't account for other things like gravity, the strong force, the weak force, and so on, then why should the theory be closed in the first place, right? So it's an optimistic, maybe slightly optimistic view, but it is the current belief of physicists. Most physicists today currently believe that quantum electrodynamics cannot be corrected, cannot be fixed, that it's just what they call an effective theory which is like an approximation, which is just some kind of an approximation. However, they believe that the strong theory, the theory of the strong force, although it doesn't have a non-perturbative definition, they believe that it is completely exact because of this phenomenon of, what do they call it? Asymptotic freedom. So they believe that the problems of quantum electrodynamics do not occur for the strong force. If you ask them point blank, do you believe that the strong force is a closed, well-defined mathematical theory with no additional elements needed? They, they obviously believe that it is, but they don't want to say that they do, because then it's a little weird. That why would the strong force exist just by itself, without the other things? But anyway, I don't want angry emails from the physics department. But what I'm saying is, as far as I have been able to figure out, this is all true, what I've said today. Okay, thanks for your attention, and I'll send you your quiz later today. Again, the assignment is due in a week or something. I mentioned that before. It's been fun teaching this class, and hope to see you again in another class.
Thank you.
You're welcome.
Thank you.
Thank you.
I'll put it on Slack. I'll put both of them on Slack. The other paper, by the way, is super important because of the fact that they looked at a quantum mechanics problem, which is somewhat of a toy model for quantum electrodynamics. And they explained why the perturbation series diverges. They actually investigated the type of the singularity of the analytic function. And what they found, it's just incredible. They found that, let me just show it to you. Where is it? This is Bender and Wu. This was Bender's PhD thesis with Wu. He's one of the old guard at Harvard, but Bender is still around, and an amazing researcher. I really like everything he does, Bender. Very practical and very deep. He's studying the harmonic oscillator. Here it is. Here's the harmonic oscillator with an extra perturbation, lambda, x to the fourth. So he's deforming the potential, okay? And he's looking for the energy levels, okay? And so the question is the perturbation series for the ground state energy, which is a power series in the coupling constant lambda, convergent? Is it convergent? The first energy level, the lowest energy level, that's what he's trying to figure out. That energy level for us was like 1/2 h bar, something like that. But in this case, it's going to be a perturbation of that, which is a power series in lambda. So, this is when they used to write papers in an understandable way. Is the perturbation series convergent? Number one, it's a question. Number two, if not, does the ground state energy, considered as a function of complex lambda, or more generally as a function of some fractional power of lambda, does it have an isolated singularity at lambda equals 0? Because of course, if there's if you can't expand in power series, it's because there's a singularity there. So is it a power of lambda singularity? And number three is the resolvent, which is H is the Hamiltonian operator, and then H minus Z inverse. That's the thing that you would use in order to figure out whether H minus Z has a kernel. If it doesn't have a kernel, that means it doesn't have an eigenvalue. So the inverse of this thing would be a well-defined analytic function everywhere away from the eigenvalues of H. Okay, it's the typical thing you do to study an operator. Considered as a function of lambda for fixed Z, is it analytic as lambda equals 0? So then they say the answer to all these questions is no. See, clarity. This is how you should write. There's no reason why people should be writing in such an obscure way, just because we're in the future from this time. More precisely, the energy levels this is quite crazy. So let me just show you what they did. So they did this in 1969, okay? And they computed numerically what the answer to this, not the perturbation theory. The perturbation theory they computed using Feynman diagrams. Let me show you. Here, Feynman rules. Here's the propagator. For us, this was A inverse. So every time there's a line, they put this, which is some inverse of some operator. And then for each vertex, look what you see, lambda, because lambda was the interaction. It was lambda x to the fourth. So it makes sense that there's lambda for the vertex. And then every time there's a loop, you need to do an integral. So they did it order by order 1, 2, and 3. And they figured out the symmetry number. This is 1 over the automorphisms of this thing. Okay. That you can flip this one, and then you can flip the 2. That's why you get 2 to the 3. So it's exactly analogous. You can figure it out here. You get they estimate the number of diagrams. They show that it's divergent. They compute the first 75 terms in the ground state energy perturbation series. Okay. This is during a time when there was something to calculate this. On an IBM 7094 in double precision mode. I don't know what that is, but it's probably really bad. So they computed all all of the perturbation series, but then they computed the ground state energy as a function of lambda. So what they found is two amazing things. Okay, the first amazing thing is they found in a different coordinate, they found a whole lattice of singularities, and they found that if you look at it in the lambda plane, this is what happens. So they're computing the lowest energy level. Okay, the lowest energy level is some real number. Okay, it's like half h bar plus something, and this function of lambda has this behavior. So it has a branch cut. Let's see, what do they say? It's a branch cut. So this is like in the complex plane, like z to the 1/2, right? Where you know the square root of z is not an analytic function around 0. You would need to pull it back to a double cover branched at the point. And so what you do is you make a cut in the complex plane from one branch point to another. And what that means, that branch cut, what it means is that there's another copy of the complex plane, which is glued to this one along that cut. And it makes like a larger surface, okay? And each one of these branch cuts is present. And so there's an infinite sequence of z to the 1/2 singularities, which are accumulating as you approach 0, okay? And then also when you go around 0, there is, where are they? There's another branch cut here. I think they haven't drawn it, where when you go around the origin, you go to another sheet. There's 3 sheets, okay, drawn here. And on the second sheet, there's no branch cuts. And on the third sheet, there's another infinite sequence of branch cuts. Okay, so there's this incredibly complicated infinite genus Riemann surface because of all these cuts. Every time there's a cut, it means there's a hole in this Riemann surface. So it's like an infinite number of donuts Riemann surface. Okay, and what are all these sheets? Okay, they determined that as you go around these branch cuts, what happens is that the energy, the function continues to be well defined and takes other values. So for example, if you were interested in evaluating the function at this point, okay, you would get the function's value here, but then you could go around one of these branch points and return here, and the value of the function would be different. Oh, actually, you would return here, and the value of the function would be different. But if you went around through this branch cut, right? You would end up on another level, and you would get, the function would have another value. If you go on another sheet, you would get another value. So this is a highly multi-valued function. That's what I'm trying to say. It's a highly multi-valued function. And why? Why is it? What they found out, what they discovered, is that these different multi-values are all the other energy levels. All of the other energy levels at this point, at this value of the coupling constant, all of the values, they are actually all values of the same analytic function. Okay, and of course, if you have this incredibly multi-valued function, it's got to be singular somewhere. And so in a sense, the reason why the first eigenvalue has a perturbation series which doesn't converge is because there are other energy levels. And because the energy levels all form this kind of infinite sheeted Riemann surface, which have these accumulating branch cuts at 0. And we're trying to expand around 0. So this is, I find this to be one of the most beautiful papers in physics. It's not very well known. I'm sure that most physicists that you ask would not be aware of this. Yeah, I'll put both of these in the Slack, but yeah, I strongly recommend. Yeah, he's the PT symmetry guy. Yeah, and in fact, his work on PT symmetry is very closely related to these issues of divergence of perturbation series. He's probably one of the world's He's one of the world experts in resumming divergent series and having techniques like that, which used to be considered to be so old-fashioned and out of fashion, except recently it's coming back in a big way in the last 6 or 7 years. Okay, yeah, sorry, I'm motor mouthing. Bye, everyone.
Can I ask actually a quick question?
Yeah, go ahead.
So when you were talking about people saying like the strong force might be considered like a completely closed theory.
Yeah, that's what they believe. Yeah.
So yeah, so what, like, how is that compatible with something like confinement for the strong force and like not being able to make accurate predictions of really low energies? Is that like asymptotic theory, I think, refers to really high energies, right? But if would it really be considered closed if you don't have like a full description because of confinement and stuff like that?
Well, but the thing is that the problem is that let me see what to say. All of the okay, so all of the perturbation theory approaches, right? What do they start with? They start with a classical field theory, and then they try to do Feynman diagram computations to measure scattering for that kind of thing, right? So that's what they're computing. Now, that's okay for, let's say, scattering protons on themselves. That's fine for that, but to some extent. But once you get into very complicated arrangements of quarks and so on, it's not so clear how to set up a perturbative calculation. Like, what are you going to perturb about? Like, there's nothing really, the whole thing is non-perturbative, right? So the question then becomes like, it's clear that there's all kinds of phenomena happening that you cannot access through perturbation theory from a classical field theory. It's clear that there's non-perturbative phenomena happening. And the question is like, is there a quantum field theory behind that? Like, if you take this perturbative quantum field theory and you somehow were able to massage it into a true quantum field theory, which would give you expectation values, a Hilbert space, and all that, right? If you could make it into that, then in principle, you could make any calculation you wanted in the strong force. But of course, they don't know how to do that, right? They don't know how to construct, let's say, Yang-Mills theory in a non-perturbative way. They only know how to access it from a perturbative way. But the question is, do they believe that it's actually there, right? Physicists believe very, very strongly in the existence of certain quantum field theories, which have very famous names like Yang-Mills theory in dimension 4, or this theory X in dimension 6, or what's another one? The supersymmetric theory for Calabi-Yau manifolds. These are theories that are not defined, but they have so much evidence that they are defined that they believe they exist in some mathematical realm which they have no clue how to access. They do not believe that about quantum electrodynamics. They believe that quantum electrodynamics doesn't exist, actually. That it's an effective theory, it's an approximative theory, which is integrating out some more fundamental degrees of freedom. But they believe that the strong force is a fundamental degree of freedom that is not an effective theory of something else. Unless you're a string theorist, of course, and then in which case you believe it, they're all effective theories, right?
Right. Yeah. So then I guess by closed we really mean like it just needs more modification, but would be complete eventually. Like it has.
They have correctly identified the degrees of freedom. Yeah.
Yeah. Okay.
They don't know how to quantize the theory. Yeah. They don't really know how to quantize it properly. It's a good question in a way, what you're asking, because they never really specify what they mean. I mean, it's like, I mean, after this paper of Dyson, which, I think it's not a coincidence that people don't know it that well. It's because they kind of avoid thinking about this issue, right? It's like at a certain point when you cannot figure out a problem, it starts to lose its pull, and they stop talking about it. I mean, you have all of these, have you noticed? I mean, there's all these popular books now about the problems with physics, the problems with string theory, and ADS, CFT, and all this stuff. What about this problem? I mean, this problem is way more interesting, I think, very practical. It has to do with things happening in the accelerator right now. And it's exposing the fact that quantum field theory calculations are calculating nothing. I mean, it's outrageous, right? I mean, it could be a scandal. I think it could be good for the popular press. I'm not a science writer, but I would encourage those of you who want to be one, write an article about this. I mean, honestly, I think it's something that people could understand. It's not so far-fetched as, trying to talk about string theory, which actually doesn't even have a model. I mean, like, why are you even bothering to tell the public about this extremely abstract string theory? I mean, they have no clue what it is. I mean, why are they so obsessed with it, right? I mean, there's so much more interesting physics that hasn't been settled.
I think maybe when the precision of the calculations really bottom out, then people might start. Then you'll kind of be forced to look at it this way. But some of them have bottomed out already, right? Like it's like, okay, well.
No, it's not close to bottoming out. No, let me show you that paper by Dyson again. There's a really cool thing that he says in it.
Maybe it'll be bad for quantum field theory if we get quantum computers soon and we can do crazy calculations. Then
no, look what he says.
Going down the wrong direction.
I should have read this part. So the divergence of the series in the real world is associated with virtual processes in which large numbers of particles are involved. Therefore, the divergence will only become noticeable when the terms of very high order in the expansion are considered. A crude quantitative estimate indicates that the terms of number 2 will decrease to a minimum and then increase again without limit, the index of the minimum term being roughly of the order of magnitude 137, because that's n. So he's saying that the size. So he's basically saying that you're only going to start seeing the terms getting bigger after 137 terms. And the difficulty increases exponentially. I think it's exponential, maybe even more, at least with our current algorithms. And we have been able to compute, I think, for this particular calculation, I think at this point, the state of the art is like 9 digits. I mean, 9 terms. I mean, I think recently it went from 8 to 9. So it's a very bizarre situation. Imagine that you have a theory like this with this level of precision, and it in principle is calculating nothing. I just find it incredible how we could have discovered such a theory.
So when he says like arbitrary numbers of virtual particles, like you're just talking about like loops in the Feynman diagram? Is that what he's talking about? Virtual processes and large numbers of particles?
Yeah, I think he's, yeah, I mean, that doesn't, it's a weird comment because, you know, it's a weird comment because these are not, I guess what he's saying is that if you believed, and this is something that Feynman apparently did believe, and I kind of believe it too in a way, that the Feynman diagrams are somehow the elementary kind of combinatorial, they are the interactions of the particles. Like I kind of like the idea that these points and the lines and so on, I feel like they are actually the nature of particles in a way. But I think that's not considered to be true. I mean, it's considered to be a mathematical formalism. It's not considered to be real. But I guess what he's trying to say is that if it were the case that these terms actually did occur with virtual particles in the real world, then the divergence would start happening with massive numbers of these particles, corresponding to massive numbers of these edges and massive numbers of vertices and loops and stuff. Whatever you are using to index your series, you know, it's going to become a giant blob of all these particles, and somehow those processes are somehow runaway processes or something. I don't know. I mean, it's a weird statement, right? Because the series is not real, and the virtual processes are not in the real world. I'm not quite sure what he means, but it's obvious how to state it in a way that makes sense. I mean, the point, yeah, well, okay, I guess he's trying to.
I have a follow-up.
Yeah, go ahead.
So it was kind of in the spirit of, I can't remember how general this result is, but if that like when you're calculating divergences in loops in your Feynman diagrams, like in general, I think higher loops, like higher loop orders, so like diagrams with 2 loops or 3 loops are going to be increasingly less divergent than the 1 loop diagram.
Okay.
And so I was just thinking about that, like if like that kind of confused me with what he was saying, but I think he's saying when you saw all those.
No. I mean, the issue about loops is more about renormalization. It's about about how to compute the coefficients at each step. But that's a separate issue. That's not a major issue. The problem is just that the definition of each coefficient is quite elaborate and requires removing infinities according to a definite process, and I would say that's a much more that's a completely, you know, it's a completely combinatorial mathematical process. It's not, I mean, I don't think it's been worked out in all cases, but there's no mystery in that. I think the definition of the perturbation theory is on solid footing. The problem is really, you know, the problem is really how are you supposed to define the theory without making reference to the Feynman, to the perturbation theory series? That's the.
Yeah, that makes sense. Like, I think I was realizing that that's a whole, like, I was talking about renormalization and something like not super related to what Dyson.
Yeah, those are in my opinion, those are just, it's just a tool bag of mathematical tricks that can be used to make sense of what the perturbation theory is requiring, and there's a huge amount that's been done in mathematics. I mean, it's a huge driver of mathematical development, but it doesn't get us beyond 1951. It doesn't get us beyond this paper. None of it does. I mean, nothing that I ever learned in physics classes or physics textbooks of any kind, nothing has ever gotten past this issue. Except I would say that there's all of the developments in conformal field theory and topological field theory. Those are different because those are non-perturbative. But as far as I know, there is no realistic, let's put it that way, quantum field theory that has been put into such a formalism. But I think that that is obviously the best hope that we have is going in that direction.
Yeah, I mean, conformal symmetry is a big ask, isn't it? Like it's for physical.
Yeah, that's right. But that's why, when you learn about Riemannian geometry, you first learn about curves and surfaces, and then you learn about Riemannian manifolds, and then, if you don't know how to, if you literally do not know how to write a quantum field theory of a circle, or the torus, then good luck to you trying to write the quantum field theory of the universe. I mean, a real physicist would reply to me saying, well, maybe there is only one quantum field theory, the one of the universe, and there's none others. I don't know, somehow I find that hard to believe. I think there's plenty of them, and I think they depend on plenty of parameters, and I think that only one of them is kind of useful, maybe, and maybe, I don't know, Dirac used to believe that depending on where you are in the universe, the coupling constant might change, which of course could be the case. Yeah, why not? Why not? I don't know. I find the focus in physics and especially in popularizations of physics is all wrong. They don't. Yeah, they don't.
I mean, I feel like it's pretty hard to start such a large paradigm shift, right? Like that's probably part of the problem is you got to get that critical mass of people who have, good avenues to go down besides what we're doing right now. And then
that's right. Yeah, no, that's right. It's yeah, that's right. It's not, I mean, I think, there's no problem really with what people are doing. It's not that what people are researching is not fruitful. Of course it is. We're doing the best that we can, but there is a part of the community. I mean, I think that there is a tendency, and this happens in all fields, of people putting their heads in the sand about certain issues. And they think, oh, well, maybe it's too difficult and maybe we can get more out of working on these problems. And that's true. Maybe it is. Yeah, I mean, maybe it's, well, okay. So there's actually one thing in this whole discussion which I failed to say, which which is my favorite answer to the question, and I would say I would modify everything that I said, except by saying one important thing, which I'm glad that it's still recording, because if I hadn't said this, it would be a tragedy, which is that There is a major group of physicists who are doing non-perturbative physics, and that is people who work on the lattice. Okay, and when you work on the lattice, that is a non-perturbative theory. And I would say that they are the ones doing the real calculations. And that's how you do calculations of like strong force among quarks and stuff. You have you try to quantize a Yang-Mills theory on the lattice. So you don't really have any smoothness. You don't have any. You don't have differentiation and all that stuff, and everything is finite. And I think I actually think that's above all, that's the best place to go in. The place where mathematicians cannot be found. That's the plot. That's the part where mathematicians don't enter, generally speaking. But I think that's where it is. I think that probably, yeah, probably the big breakthrough that's going to come is going to be from the lattice. That's what I think. The problem is that they're not doing it in a way that they need to upgrade their technology. They need to upgrade their technology of the lattice so that they can get rid of the dependence on the particular lattice that they're using. I think. Anyway, okay, everyone, have a good summer.
Thanks.
Thanks for a great course.
You're
Thank you.
welcome.
Thank you.
You're
very much.
welcome.